So first off, let's talk about the fundamental atomic structure. Atoms are the basic unit of matter. Um, every type of matter, like every type of thing on the periodic table of elements, has its own distinct qualities to it. And those qualities are the way they are because of the structure of each element on the periodic table. Everything in nature is made of atoms. Atoms consist of primarily a nucleus, which in the nucleus, the center of the atom are protons and neutrons, each of which have their own subsequent particles that are considered to be more fundamental than the protons and neutrons. Really, at the level of radiography, we just need to understand that there are protons and neutrons in the nucleus of any atom. The number of protons and neutrons will vary, and that's part of what gives atoms uh, their distinctive characteristics. The protons in the atom are noted on the periodic table of elements by the letter Z. Z is the atomic number or the number of protons. Protons are a positively charged particle, and they have a weight of 1 atomic mass unit or 1 AMU. Neutrons are neutrally charged, and before you break them down into their own individual components of gluons and quarks, quarks being the matter particles that compose these atomic nuclei, and gluons being the particles, the theoretical particles that carry the gravitational force. Neutrons are actually kind of an interesting particle. They're neutrally charged, but if left in open space for a period of time, only minutes, I believe the number is like 6 minutes, they will spontaneously decay into a proton, an electron, and an electron neutrino, which is this funny little small particle that's essentially massless and only really is talked about when we talk about the nuclei of atoms decaying. So that's the nucleus of an atom, protons and neutrons. Protons are positively charged and are considered, for the most part, fundamental. Neutrons have a no charge, hence the name neutron, neutral, no charge, and they are comprised of a proton, an electron, and this little guy called an electron neutrino. That's the nucleus of any atom. Orbiting the nucleus of an atom, and orbiting is kind of a funny word, but we'll get to it later. At least in the picture here, you can see that it looks a lot like these things orbit the center of an atom, much like the planets of our solar system orbit the sun. In all reality, it's a little bit different than that, but to picture it like that to start with, I think is a healthy thing. So electrons are at least from the electromagnetic standpoint, the polar opposite of a proton. They have a negative electric charge, and protons and electrons are attracted to each other, whereas electrons and electrons are repelled from each other, and protons are repelled from each other. That's kind of a funny topic we can get to later. But it is just that electrons have a negative electric charge. They have the same but opposite electric charge, protons positive, electrons negative, but electrons don't have the same mass. The electron's mass is about 1/2000th of 1 atomic mass unit. So it would take approximately 2,000 electrons to equal the same atomic mass, or and weight's a bad word, but we can say in our context kind of atomic weight. Take 2,000 electrons to equal the weight of a single proton. So that's our fundamental structure of atoms: the nucleus surrounded by shells of electrons. Now, I haven't told you how many electrons hang out in those shells. We'll come to find that at a later date, but we can just accept, hopefully, that there is a nucleus made of special particles, protons and neutrons, each having their own special qualities: protons a positive charge, neutrons no charge, and orbital electrons that have an equal and opposite charge to the proton. So there you go. The protons and neutrons each have approximately 1 atomic mass unit of weight. Now, it's not exactly, for example, the neutron's not exactly 1 atomic mass unit. I told you it was made of a proton plus an electron plus a neutrino, so it's obviously going to have to weigh a little bit more than a single proton does. But for all intents and purposes, we can just say for neutrons, protons, 1 atomic mass unit. It's one of the other numbers you'll get on the periodic table is the atomic mass unit, noted with a capital A. So if you're keeping track, capital Z for the number of protons, capital A for the number of total particles in the nucleus. We call that the atomic mass. The electrons orbit. The electrons are in fixed, semi-fixed orbits around the nucleus of an atom, and the electron at least in this context, is said to have a number of 0 atomic mass units. Now, electrons do have mass. I just told you they were approximately 1/2000th the mass of a proton, but it's a very small number, so for our purposes, we can nearly say 0. Electrons reside in shells. These shells are given the letter designations of K, L, M, N, O, and so on. The closest shell to the nucleus of an atom is called the K shell. The K shell is special because it can never hold any more than 2 electrons. These 2 electrons will be repelled from each other, so they'll be on opposite sides of the atom from each other on that K shell. And the K shell electrons are the ones that are closest to their ground state or closest to their lowest energy state. They are bound in orbit by the most amount of energy, more than the other subsequent orbits. The L shell is bound with less energy than the K shell electrons. The M shell is bound with less energy than the L shell electrons, and so forth until you get all the way out to the outermost shell of the atom. The outermost shell of any atom will never hold more than 8 electrons. It will always seek to try to find 8 electrons, and it'll arrange them into pairs of 2, so 4 pairs of 2. An atom with a completed outer shell, completed valence shell, will not seek to create or break any bonds with other atoms. It will be non-interacting. Good example of that are the noble gases on the far right of the periodic table of elements, gases like argon and xenon gas. Now, the big reason why I'm making this video prior to the radiation protection section is that we need to understand the basic structure of atoms in order to understand why X-rays or certain kinds of electromagnetic radiation are harmful to the body. The reason X-rays and other types of high energy electromagnetism are harmful to the body is because they can ionize matter. So I've just described what matter is. Matter is made of atoms composed of protons and neutrons in a nucleus and electrons in orbit. Normally, a neutral, happy atom has the same number of electrons as it does protons, and those numbers match, and the atom is electrically neutral. Well, if enough energy is deposited into an electron, it can raise that electron up a shell level or more. If an electron is at the outermost shell level, or is given enough energy from somewhere else within the atom, the electron can be, in essence, ejected from the atom at a high rate of speed. So that brings me to why it happens. Electrons have a currency by which they exchange energy. Just like we exchange dollars for services and items, electrons exchange photons of electromagnetic energy as their currency. When an electron loses energy and moves down shell levels, it does that by emitting a particle of light called a photon. The amount of energy lost by the electron is equivalent to the amount of energy released in that photon of light. And the converse thing is true. That photon leaves that electron and it finds its way through space and eventually interacts with another electron in space and deposits its energy into that electron. That would cause the receiving electron to be raised from its current energy state, and it may in fact have enough energy to eject that electron from an atom. So electrons, they emit photons of light and they absorb photons of light. Photons of light, electromagnetism, are a form of potential energy. They don't do anything as they're traveling through space, but once they reach matter, they interact with the electrons of matter, raising their energies. And in some cases, if they have enough energy to give up the X-ray, they can potentially eject an electron from the orbit of an atom. So that's shown here in this image. An X-ray photon comes in, it strikes an electron of an atom. If the X-ray photon has enough energy, if its wavelength is short enough, if it's energetic enough, it can put enough energy into that electron to eject it from its orbit. We call that ionization. So ionization is radiation hitting an electron. The electron is knocked out of its orbit. And in an ionized atom, when an electron leaves, the atom gains a charge. It was electrically neutral, but it lost one negatively charged particle, so now it's got a charge of +1. The free electron has a charge of -1, and now you've just created two things from one thing. So you have an electron in space with a charge of -1, and a left behind atom in space with a charge of +1. You now have an ion pair. This is the primary reason why X-rays are harmful to biologic organisms, because everything's made of atoms, but you can ionize the atoms of a desk and nothing happens to the desk because the desk doesn't need to change. You can, but if you ionize the atoms of, like, let's say somebody's DNA, and their DNA has to replicate and build new cells, well, you've just changed their DNA by doing the ionizing, by creating an ionization event. You've changed their information, their DNA. So when the cell goes to replicate itself, boom, you've got a different copy than you had before. This is the primary reason why X-rays are harmful. Now, X-rays are just electromagnetic radiation, so they're similar in their nature to things like radio waves and visible light. It's just that they carry much more energy than radio waves and visible light do, so they can do damage to the body that radio waves and visible light just couldn't even begin to approach. As I stated earlier, the electrons are organized into shells, the K shell being the lowest shell level shown at the top of this graph. It's given a shell number of 1. The way to calculate shells, except for the first shell and the last shell, is by the formula 2n squared, where n is the shell number. So using that formula, you can see pretty quickly here that the L shell can hold 8 electrons, the M shell can hold 18, the N shell can hold 32, O shell 50, the P shell 72, and the Q shell 98. It's important to note that each shell will fill up and spill over, electrons will spill over into the next shell as the atoms get larger. And it is also important to remember that the inner shell will only ever hold 2 at the most, it's full after 2, and the outermost shell of an atom will only ever hold 8 electrons at its most, and it will always try to seek to have all 8 electrons in that outer shell. And the shell number is considered the principal quantum number, and again, we use that number to calculate the number of electrons possible in each shell of an atom. Atomic facts. An atom that's stable is electrically neutral. Atoms are inherently unstable if they're not electrically neutral, and any atom that's not electrically neutral will try to become neutral by adding electrons to its shell levels until it has a neutral balance. As I stated earlier, the outer shell of an atom will never contain more than 8 electrons, and the atomic number, capital Z, of an atom is equal to the number of protons in its nucleus. Types of ionizing radiation. The type that I was talking about throughout the video here is electromagnetic radiation, which we mostly talk about as X-rays, but also consists of gamma rays and some sub-ionizing types of ultraviolet radiation that can still perform harm to the body. The type that I didn't discuss during this video is particulate radiation, alpha particles and beta particles. These are fundamentally different from electromagnetic radiation in that they are parts of the nucleus of an atom being essentially fired away from the atom at high speed. So pieces of matter being shot away at high speed, whereas electromagnetic radiation is not matter, it's potential energy moving through space. Particulate radiation has the potential to do much more harm to the body than electromagnetic radiation due to its massive nature. Alpha particles are essentially a helium nucleus flying through space, two protons, two neutrons, whereas beta particles are essentially a high-speed electron flying through space, both of which are massive, both of which have electric charge, and both of which can cause more harm than electromagnetic radiation. The primary focus of radiation protection courses in limited radiography talks about electromagnetic radiation, but it's nevertheless important to not overlook particulate radiation. So that concludes my video. I hope you learned something, and I hope this prepares you a little better for the topics of radiation safety in the coming months. Thank you.